In this video, I'm going to talk about completing the square and the vertex formula of quadratic functions. A general quadratic function is given by y equals to ax squared plus bx plus c, where a, b, and c are arbitrary real numbers such that a is non-zero. If a were 0, then this term will be gone, and we are left with y equals to bx plus c, which is a linear function instead of a quadratic function. An example of a quadratic function can be given by y equals to 2x squared plus 12x minus 7. Completing the square means that we want to rewrite this quadratic function such that it is now a sum of a square and a constant term. And we want to make sure that there's no linear term in this expression. Why do we want to do that? Great question, and we'll address it later in this video. Because of the equal sign, we cannot just have an x here. Otherwise, if b is non-zero, then these two functions will never be equal to each other, contradicting the equal sign. Instead of just a simple x, we are going to write x minus h in this position, where h is a real number. When we look at this expression, you will notice that the coefficient of x squared is 1, while the coefficient of x squared is a on this side. We have to make sure that the coefficient of x squared match up because of this equal sign. So we have to multiply an a in front, where this a is exactly the same a as before. To complete the quadratic function on the right-hand side, we write k for the new constant term there, so that a, h, and k are real numbers. Since this a is the same as the one before, we have the same condition that a is non-zero. To complete the square for this example, we will get 2 times of x minus negative 3 all squared plus negative 25. In other words, a is 2, h is negative 3, and k is negative 25. To verify the correctness, all we need to do is to simplify and expand the square. We have 2 times x plus 3 all squared minus 25, and after expansion we get 2 times of x squared plus 6x plus 9 minus 25. Distribute, we will have 2x squared plus 12x plus 18 minus 25, and it gives the same expression as the left-hand side. Okay, so this equality holds true, but how did we get this completing square expression at the first place? The main tool of completing the square is to use two of the most important algebraic identities in the world, introduced in an earlier video. To illustrate the process of completing the square, I'm going to start with the example from the last page. We had y is equal to 2x squared plus 12x minus 7. First, we factor out the leading coefficient 2 out of the quadratic term and the linear term, so that we get 2 times of x squared plus 6x, and then keep the constant term at the end, minus 7. This first step is to ensure that the coefficient of x squared inside the parenthesis is 1. Next, compare what we have inside the parenthesis with the identities. We have already got x squared, so y must be 3, so that 2 times 3 times x is our 6x. Hence, we are going to write down 2 times x squared plus 2 times x times 3, and in order to continue with this identity, we have to add 3 squared. But we have to maintain the equality unchanged, so we need to subtract 2 times of 3 squared so that they would actually cancel out each other, and then keep the original constant minus 7 at the very end. We can now rewrite this parenthesis as a perfect squared. So we have 2 times of x plus 3 all squared, since 3 is our y. And then minus 18 minus 7. And lastly, remember that we want to rewrite this as a times x minus h squared, and then plus k. So this is now written as 2 times of x minus negative 3 all squared, and then plus negative 25. This finishes the process of completing the square for one example, but we would like to do it for more general quadratic functions. This time, we will start with y is equal to ax squared plus bx plus c, where a is not equal to 0. In the first step, we factor out the leading coefficient a out of the quadratic term and the linear term. So we will have a times parenthesis x squared plus b over a x, and then keep the constant term plus c at the end. Notice that when you distribute, you will exactly get ax squared plus bx back. Next, we compare the expression inside the parentheses with the identities. We see that we already got x squared, so we must have b over ax equal to 2xy. In other words, we will have 2y equals to b over a, and y must then be b over 2a. Rewriting this expression using this structure, we get a times x squared plus 2 times x times b over 2a, so that this term is exactly b over ax, but at the same time it fits 2xy format. In order to perfectly match, we have to have y squared at the end, which means that we have plus b over 2a all squared. However, this is an equality, so if we add an extra term, we are changing the value. We have to balance it out by subtracting a times of b over 2a squared, so that this term and this term will cancel. Lastly, we also need to do plus c, so that the constant is preserved. Applying the identity to simplify this expression, we get a times of x plus y, which is b over 2a all squared. This constant can be simplified to plus c minus b squared over 4a. This is because b squared over 4a squared is the expansion of this fraction, and 1a in the numerator and 1a in the denominator will cancel out to form 4a instead of 4a squared. Recall that the goal of completing square process is to get a times of x minus h all squared plus k, so that there's no linear term. We found that we are basically done. We have a matched with this a, x minus h matched with this x plus b over 2a, perfect squared, and the constant is now c minus b squared over 4a. From this line, we can also obtain a formula for h and k. Namely, h is equal to negative of b over 2a, so that x minus h becomes x plus b over 2a, and k will be equal to c minus b squared over 4a. These two are often referred to as the vertex formula. Why? I'm going to explain it in the next slide. The process of completing the square turns a general quadratic function into this particular form. This form allows us to detect the type of transformations from y equals to ax squared. If you need a review, you may refer to my previous video on graph shifting. Specifically, this quadratic function has undergone a horizontal shift by h units, as well as a vertical shift by k units. If you look at the graph, when a is less than 0, then the parabola y equals to ax squared will open downwards, and hence, with the shifting, the new curve will become this, where the new vertex is at h, k. If a is bigger than 0, then the parabola y equals to ax squared is opening upwards, and so the new parabola will become this, with the vertex also at h, k. Since h, k is always the vertex of the parabola, we will call this formula the vertex formula of the quadratic function. Back to the example earlier in this video, we had y equals to 2x squared plus 12x minus 7. If we apply this vertex formula, then h would be equals to negative of 12 over 2 times 2, which is simplified to negative 3. K is equal to negative 7, which is our C, minus b squared over 4 times a. This is simplified to negative 7 minus 18, which is negative 25. Hence, completing the square of this quadratic function will give us a, which is 2, times x minus h, which is negative 3, all squared, plus k, which is negative 25. Isn't this exactly the same as what we got previously? Therefore, if we know the vertex formula by heart, then we could skip some of the algebra and finish the completing square process right away. Thank you for watching this video. If you like it, please subscribe to our channel and we will learn more fun math together. Thank you.